Welcome everyone to AGU Plenary Lecture. This AGU Plenary Lecture is aiming to provide lectures on latest worldwide topics with easy and clear explanations. This year, 5 special speakers from different areas are invited during this JpGU-AGU joint meeting. Today, we have Dr. Aki Takigawa from Department of Earth and Planetary Sciences, the University of Tokyo. Her presentation today entitles Life Cycles of Dust in the Galaxy. Dr. Aki Takigawa, would you please begin your talk?
Thank you very much for your introduction, and thank you very much for giving me this opportunity to give a plenary talk here. And also thank you very much for everyone joining this talk, and please enjoy my talk with your lunch. And I'm Aki Takigawa, University of Tokyo. Today I'm going to talk about the life cycles of dust in the galaxy. And I start my talk why we should think about the galaxy and why we should think about dust. Here I show the life cycle of stars. Stars, the evolution path of stars depends on their masses. The stars formed from the molecular cloud here, where the dense gas and dust cloud. So I should define what is dust here. So it's very general, but the dust is small solid particles. And how small, it is difficult to define clearly, but mostly less than 1 micrometers. And there are larger grains also, but I will discuss in the last several slides in this talk about the size of dust. But basically, it's small, less than 1 micron. And there are various kinds of dust, minerals, ices, and organic matters. And every small solid, we can call dust. During the collapse of molecular clouds and the formation of protoplanetary dust disk, a protoplanetary disk is consists of young star and surrounded by the gas and dust disk. During the formation of protoplanetary disk, some of the dust in the molecular cloud was distracted. For example, vaporized into gas or or just physically distracted. And the stars spend, and also in this protoplanetary disk, dust newly formed from the hot gas. And from this protoplanetary disk, planets like Earth and Mars formed. And the stars spend most of their lives as main sequence stars, burning hydrogen. And after the main sequence stage, stars evolve into dying stars. For low or mid-mass stars, they evolve into red giants and finally die as white dwarfs. But for massive stars, they evolve into red supergiant and finally explode as supernovae. At the end of these stars, so these dying stars eject a lot of hot gases, and from the hot gas, the solid particle dust formed as well. And the gas and dust are injected into the interstellar medium. And in this ISM, the dust are distracted as well. The main cause is the supernova explosion and shockwave propagation may distract the dust. And then some dust formed molecular cloud, and from that molecular cloud, the next generation stars and planets formed. So if we want to understand the planet formation or life cycle of stars, dust grains is a good proxy for that. And why? And one very important point that reason that we should think about dust is that is the carrier of metallic elements. Here, I choose the fluxation of metallic element in the interstellar medium and the fluxation of the metallic element in the gas phase as the function of condensation temperature. That means the volatile elements are plotted on the left and refractory elements are plotted on the right. Some element like nitrogen is almost all nitrogen in the gas phase. This line is 100% of the element is in the gas phase. Like carbon or oxygen, about 70% of them are in the gas. On the other hand, more refractory elements like silicon, magnesium, iron, about more than 90% of them are not in the gas phase. Only a few percent of these elements are in the gas phase. The remaining are in the dust. So in other words, most of the silicon, magnesium, iron are in the dust. So we have to study dust grains if we want to know what the elements are formed and evolved in the galaxy. And another and probably more important point is for us is that dust is the building blocks of the solar system. So as I shown before, the dust is from the dust and gas disk our planet formed. But the dust, and the dust is the smallest component, most fundamental component for the planetary formation. But so dust forming the solar system can be classified into three. Dust grains formed in the protoplanetary disk. I call protoplanetary dust. So protoplanetary dust are purely formed in the solar disk after the birth of the sun. But the dust forming the planetary system is not only the protoplanetary dust. There are two more components. One is interstellar dust and another is circumstellar dust. The circumstellar dust is dust grains formed around the dying stars and survived a lot of processing in the interstellar medium and the protoplanetary dust. And the interstellar dust, this is different from the circumstellar dust. Interstellar dust is here. I define the interstellar dust as dust grains formed in the interstellar medium. So the circumstellar dust are distracted in the interstellar medium, and we formed a new dust in the interstellar medium. So these we have to, if we understand these three kind of dust grains, how they form and how they evolve, we may understand dust grains forming the solar system. So there are basically two approaches to study the dust grain in the galaxy. The first one is astronomical observation. The dust grains out in the circumstellar environment like red giant or protoplanetary disk outside the solar system. So such dust cannot be obtained by and analyzed in the laboratory. So we use the light. The dust grains around the stars are heated by the radiation from the central star, and heated dust re-emit infrared light, reflecting their crystal structures. Here I show the example. So the as a major silicate dust, I showed the structure of crystalline and amorphous Mg2SiO4 phosphoride. So please see this figure. This is the infrared spectrum of various minerals with different crystal structures and chemical compositions obtained in the laboratory. The dust around the stars re-emit the infrared light, and the spectra depends on their chemical composition, crystal structure, size, morphology, and aggregation state. For example, if there is a phosphoride dust, crystalline Mg2SiO4 dust around stars, we will see such kind of sharp peaks around at 10 micrometers in wavelengths. But the crystalline structures of phosphoride is not crystalline but amorphous. We expect the dust feature is like this, very broad and single peak of 10 micron. So the crystal structures strongly affect the infrared spectral features of dust. Also, if the composition is different, phosphoride and sulfides show clearly different peaks, different peak positions. Like silica is also clearly different. So we use this difference and we analyze the observed spectra and evaluate and estimate what kind of dust around the observed stars. So this is an example of observed dust features. This is from the famous Protoplanetary disk. So this solid black curve shows the observed spectrum, and the spectra of minerals obtained in the laboratory are compared here. So the main dust in this protoplanetary dust disk is amorphous silicate, and there's some amount of phosphoride, amorphous carbon, and water ice. So and on the right, I show another spectra in blue. This is the from comet Hale-Bopp in our solar system. So not only the extrasolar system, but also within the solar system, we can observe the dust and estimate what kind of dust there. And compared with the protoplanetary disk and the comet Hale-Bopp, both objects have phosphoride dust, and the spectra are very similar. That means in the protoplanetary disk, the comet-like objects are also present. So we know the similarity between our system and another planetary system. And another observation which I should mention here is the spatial distribution of dust. So the spectra I show here is from circumstantial dust in the disk, but it's kind of average of all the dust in the protoplanetary disk. But there should be some variations in the disk because disk is so big and the temperature, gas pressure conditions are different. So, but it is very difficult to observe the spectra from the different locations of the one protoplanetary disk, because protoplanetary disk is generally small, and even if we use the best instrument, best telescopes, it's not easy to resolve the spatially. But there are a few studies for that. In this paper, they observed the 3 protoplanetary disks, and they resolved the very inner region of the disk and observed the emission from the outer region of the disk on the right. So if you compare the left and the right, you may see the spectra on the light is have more sharper peaks than the right outer dust grains. So that means that the sharper peaks reflect the crystallinity of the dust. So there are several experimental works on crystallization of dust in the circumstantial conditions. I show the example. In this paper, they simulate the protoplanetary disk conditions and perform the experiments for crystallization of forsterite. So at this temperature, with after heating the amorphous forsterite for some duration, the forsterite easily crystallizes and the peak becomes sharper and sharper. So this observation shows the amorphous silicate in the outer region going to the near the center of the near the center of the disk and heated by the stellar radiation or accretional heating and crystallize. So not all the dust is crystallized, but some of them are crystallized. Okay, so another way to study the protoplanetary dust is laboratory analysis of meteorite, cometary dust return samples. Uh, so there are various kind of components in meteorite. So relatively large components like these roundish components called contours. These are secondary phases. I mean, they experience melting. So there is a precursor material forming such contours. So when we see the matrix between the contours, so this is an image of matrix from different meteorite, Ashford 094, but you may see the very tiny grain there. The grain size is much less than 1 micrometer. So these small grains are probably the protoplanetary dust. Dust. I mean the dust grains formed in the very early solar system and condensed from the gas. And also the good target is cometary dust. Cometary dust is the dust from comets, but the comet the temperature of the comet is very, very low because they are outside the outer region of the solar system, so they preserve relatively primitive materials. So I want to understand the building blocks of the solar system. We should focus on the least altered and the very most primitive material. So I focus on the cometary dust here. So when we look at the cometary dust, the most important dominant component is called gems. So these small particles. So like the size is less than a few hundred nanometers in diameter. So gems is glass with embedded metal and sulfides. So gems so here I showed the image of typical gems. The grayish region is amorphous silicate, and the black dot are iron nickel metal or sulfide. So this is the probably most primitive materials we know in the solar system. And the similar materials are observed in the primitive meteorite. This is from carbonaceous chondrite, but the amorphous silicate contain more iron compared with the cometary dust. So the origin of the gems is under debate still now. So one scenario is that they formed by condensation in the protoplanetary disk. So hot gas cooled in the solar system, and these kind of materials are formed. Or another scenario is amorphization of circumstellar dust in the interstellar medium. So that means the gems formed, the precursor material of gems is formed in the dying stars, and during the travel in the interstellar medium, they are irradiated by some energetic particles and amorphized. So that's the two scenarios. So, so if we perform the we perform the experimental studies in laboratories, so to determine the origin of the gems. I don't go into detail about the experiments, but basically we produce the very high temperature plasma, 10,000 kelvin something, and the materials are vaporized in this high temperature plasma and cooled at very high cooling rate, so quenched. So we obtain the nano particles. So if we control the gas composition of starting materials as solar abundance, we obtain this kind of. I'm sorry.
Any problem?
Yeah. Sorry, my keynote is shut down. So please wait a minute. I reopen.
Okay.
So if you have any questions, please ask me anytime. Okay. Okay.
Okay, clearly.
Okay. I continue. So again. Sorry. I don't know why, but keynote is closed again. So let's share the keynote.
Okay.
Okay.
Okay, I can see clearly.
So I continue. So so this is the wow. Okay, so I share the PDF file instead.
Yeah.
Does that work?
Okay, I can see.
Okay. Okay, so this is the condensate. So you may see the grayish region. These are amorphous silicate, and the black dot. These are iron metal. So these grains are more fluffy than the observed gems, but probably the gems are experiencing some compaction. So we can synthesize very similar materials like gems. So so what we shown that is so gems-like materials can form by condensation. We don't deny that it's not impossible to they formed by irradiation, amorphization, but at least they can form by condensation. And so when we compare the infrared spectra of condensed materials with gems and some young objects like molecular cloud and protoplanetary disk, they're very well very similar between among these spectra. So probably the most primitive material can be the gems-like materials condensed in the solar system. Then I move on to the next topic, the circumstellar dust. Circumstellar dust around dying stars. So there are several dust sources in the galaxy. So low mass stars and high mass stars. From both high and low mass stars are important sources of the dust. But here I compare the mass injected from the low mass and high mass stars. And in our galaxy, Milky Way galaxy, the low mass contribution from the low mass stars are higher than the high mass stars. So in this talk, I focus on the low mass AGB stars. So there are two types, three types or two types of the AGB stars. The difference is CO ratio. Here I show that the observed gas distribution around the oxygen-rich and the carbon-rich AGB stars. This is a take we took with ALMA, and this is also another group take with ALMA. So from around these two types of the star, different types of dust formed. Around the oxygen-rich stars, that means the C/O ratio is less than 1, silicate and oxide dust formed on stars, and carbon-rich stars, the amorphous carbon or silicon carbide dust forms. And both types of dust grains can be observed as presolar grains in the laboratory. So I mean, we can find the survivors of two types of dust as tiny grains in the meteorite. So how we so the origin of each presolar grains were determined by isotopic analysis. So here I show the oxygen isotopic compositions of presolar oxide and silicate grains, and here I show the nitrogen and the carbon isotopic compositions of presolar silicon carbide. So there are several groups of the isotopic compositions, and each groups are explained by the different nuclear synthesis in the stars. For the main major, most of the grains are from low mass AGB stars, and a few some of the presolar grains are from supernovae. So today I focus on the oxygen-rich dust. So I want to show some example of presolar grain identified from the primitive meteorite. So in other words, the survivors of circumstellar dust. So in the first talk, I don't know, but so it's different. It's impossible to take the circumstellar dust and analyze in the laboratory, basically. But the exception is presolar grains. We can analyze and obtain the detailed quantitative information from the circumstellar dust. So there are several kinds of presolar silicate. This is olivine, this is anthracite, and aluminum-rich amorphous silicate, but most of them are amorphous silicate. And in the case of oxide, this is my favorite presolar grain. This is a presolar corundum grain, crystalline aluminum oxide grain. So not only the aspect composition, but also the morphology or crystal structures recall their formation conditions or formation processes. So this grain have very clear, developed crystal faces here or there. These crystal faces reflect the indicate that this grain formed and grows around so this grain formed by direct condensation from the gas. So I mean, this grain is not crystallized of the amorphous dust, but they directly condense as crystalline dust. So and also there are variations of presolar quantum grains, but I, and so I showed the amorphous silicate and several crystal presolar silicate grains, and this is the presolar aluminum oxide grains. And I want to compare this analysis with observation. Here, I showed the mid-infrared spectra of dust grains from silicate-rich AGB stars and aluminum-rich AGB stars. About 60% of oxygen-rich AGB stars, they showed the characteristic peaks at 10 and 18 microns. These are from the amorphous silicate. So, and also the quantum is also observed. About 40% of oxygen-rich stars shows the strong feature at around 13 micron. This is from the quantum dust. So basically, we have the presolar grains. We have some good sample for good sample of the typical sample of the circumstellar dust. And so another topic is the presolar grain I show here is relatively large. I mean, these grains are more than 1 micron in size. This is very, very big. It's not easy to form. But so here I show the same image I showed previously. This image is from oxygen-rich aluminum-rich AGB star, and this yellow region shows that aluminum oxide molecules are there and distributed within a few still ready from the star. The aluminum monoxide molecules disappeared suddenly from the gas phases. Probably this is due to the dust formation. And from the dust mass of this star, it's indicated that the aluminum oxide should stay this region for several pulsation cycles. So this kind of AGB star is the pulsation is continuously occurs. So the theoretical studies of dust growth during the pulsations shows that this graph shows the size distribution of aluminum oxide dust around an AGB star. This figure shows that aluminum oxide can grow to some micron in size after 12 pulsation. This is the get size, comparable size with the presolar grain. So, but it requires relatively high gas density conditions. I didn't link the second grain. Okay, right. This is a little bit old version. Sorry. Fine. Okay. Okay. So finally, I want to discuss about interstellar dust. So here I shows the size distribution of dust in the interstellar medium. So this is to explain the several observations. The size distribution should be like this. So this is 2.5 microns. So 0.2 micron or something like that. So the point is there is no so most dominant grain size is about 0.1 micron in size, and larger grains is not is absent in the interstellar medium. So what does it mean? So we observe the larger grain and presolar grains, and some larger grain could form around the stars, but there's not many large grains. So this is because dust is distracted in the interstellar medium. Here I compare the timescales of dust production in the galaxy and the dust destruction timescale of the galaxy. So it's about more than one order difference between them. So the dust lifetime scale in the galaxy is too short. So the destruction processes of the dust in the interstellar medium is basically there are two types of destruction processes. One is dust gas collisions. Dust gas collisions is the main cause of the amorphization of dust. And this is the observational study to estimate the degree of crystallinity of interstellar medium silicate dust. So they showed that less than 2% of silicate dust is crystalline. So again, the difference of crystalline dust and amorphous dust is the degree of ozoning of the atoms in the dust. So this amorphization may occur the high velocity gas dust collisions. So the dust is exposed against accelerated gas molecules like hydrogen proton or alpha particles. So these hydrogen or helium ions are accelerated by the supernova shockwave propagation. So the accelerated gas is hit on the dust surface and damage the crystalline structures. Like this is the experimental study how the crystalline structure changed due to the hydrogen irradiation. So the beautiful surface is gradually damaged, and this region is completely amorphized, and some vesicles appear on the very surface. Also, the chemical composition is changed due to the irradiation gas dust collisions. The and the sorry. Okay, so this shows the oxygen silicon magnesium silicon ratio is changed due to the irradiation. So as this is origin, I think, and the magnesiums and to silicon ratio decreases as the dust is irradiated. So not only the structure but also the chemical structure changes the gas dust collision in the interstellar medium. Another important destructive process in the interstellar medium is grain-grain collision. It's more simple, just grain and grain collide and sputtered or shattered away. So this is a theoretical estimation how the grain-grain collision occurs and how effective. The fraction of destroyed, that means how much amount of dust destructed by the one supernova shockwave propagation, and they estimated the for larger grains I should this okay, so for grain collision is larger grain is more effectively destroyed by grain collisions. So but it is very difficult to determine or to evaluate how the grain-grain collision occurs in the industrial medium from the natural samples. But we have one good example, probably indicating that grain had experienced grain-grain collision. So this grain is a presolar quantum grain. So this is the same grain I showed before. This grain is formed by direct condensation from the gas. But if we cut this grain, if we made a thin section, very thin film from this grain and observed in the trans TM, we can see the interior structures, and we found that there is a cavity here. Maybe we can see here as well, but this grain have a nano-sized nano crater. And this grain also have some features that may have experienced a transient heating because some magnesium element concentrate as some small regions, and these magnesium concentrated regions is probably related to this cavity formation. So so in this case, probably the energy is less than the critical energy that shattered with this grain, and just a small crater remained on the surface. So, but so probably we can find more signatures that grain-grain collisions if we analyze each presolar grain in detail. Finally, I want to talk about a little bit about the dust formation in the industrial medium. As I showed in the first slide, the metallic elements are depleted in the gas phase and should be in the dust. But as I showed in previous few slides, dust grains are destroyed or spotted. So that means we should reform the dust grains in the industrial medium just after destroyed. So unfortunately, there are only a few experimental works simulating the dust formation in the molecular cloud because it occurs at very low temperatures. And they show no clear structural or spectral difference between low temperature condensate and high temperature condensate. We should study the such process more in detail to understand what happened, to understand the dust formation in the industrial medium, to account the mass and dust depletion depletion of the element in the gas phase in the industrial medium. So I want to summarize my talk here. So I talk a lot about the dust grains in this lecture, the dust planetary dust and circumstellar dust and interstellar dust. And for further understanding of dust grains, which is the most fundamental building blocks of the solar system, I write a few points. So what we know is that the combination of detailed analysis of presolar grains and astronomical observation of circumstellar dust or circumstellar environments works very well. We know a lot, and we now can discuss a very detailed dust formation processes. And also the good point is that due to the ALMA, we will obtain more observational data on dust forming regions. So I'm very excited about that. And but we should understand the variation. We have not understand what caused, what made the variation of amorphous silicates in the meteorite, cometary dust, and circumstellar interstellar medium. So the point is, we don't know how we can distinguish amorphous silicates formed in the interstellar medium from the amorphous silicate formed in the protoplanetary disk, and we don't know how different structure made so the amorphous silicate formed by alternation and amorphous silicate formed by condensation are so the similar structure or different structure, we don't know at this moment. So we have some knowledge about that, but we don't fully understand. And formation and the characteristics of interstellar dust is poorly understand. This is this similar point. We should distinguish interstellar dust from protoplanetary dust to discuss this point as well. So I may talk a little bit too much in detail this talk, but take-away message is the studying the life cycle of dust in the galaxy may expand the history of the solar system, our solar system, back to our parent stars. Thank you very much.
Thank you very much for your interesting talk. Now, we'd like to receive several questions or comments. Please use Zoom chat box, or you can also speak directly, please. Any question or comments? You can Zoom chat box, or you can also speak directly.
Oh, I think we have a question from Luke-san.
Ah, yes, please.
Okay. So may I read that? Hi, Aki-san. Thanks for a great talk. Thank you very much. How does the flux of dust to Earth vary as our solar system moves through our galaxy? And do we see or expect any effect we could use in composition? Are we seeing a representative sample today? Oh yes, that's the great point, important point. So I don't know about the flux of dust to the Earth, but so at this moment we don't know the presolar we already have represent the all the circumstellar dust, or there is some sampling bias. And what we know is that if we average the, so I should show the, if I average the oxygen or some isotopic compositions of presolar grains, if we average these isotopic compositions, we never get a solar oxygen isotopic composition. Probably the average values are here. So clearly that there's some process that change the average oxygen composition in the solar system. So that's kind of why I think I should study the dust formation around the stars, because we don't know what kind of dust and what the variation of the circumstellar dust. So if we collect the presolar grain and analyze it a lot, we don't know this is the typical sample of the circumstellar dust. So we need more studies on the dust formation around the stars to answer what kind of sampling we did at the early stage of the solar system formation.
Okay. So again, thank you very much for your lecture. Everyone, thank you for coming today. Now we close the AGU plenary lecture. Thank you.